Hello, everyone. Welcome to another episode of Future Intelligence Talk. Today, we have another excellent speaker from robotics, Dr. Antonia Tzemanaki from Bristol Robotics Group. Antonia is a senior lecturer and researcher at the Bristol Robotics Laboratory, known for her work in haptics and medical devices. Her research focuses on robotic manipulators and medical robotics, with an emphasis on developing tools that can enhance surgical precision and minimally invasive procedures. Today, she is going to talk about haptics, tactile sensing, and dexterous manipulation and teleoperation with the end user in mind. In the end of the speech, you will have some time to ask questions, but feel free to type down questions in chat if you have any. And the talk will be recorded and published in our YouTube channel as well. And Antonia, over to you.
Thank you very much, Chapman. So good afternoon, everyone. I'm not going to reintroduce the topic and myself. Chapman did a really good work doing so. But there you can see my email in this slide, as well as the link to my group's page. If you want to have another look, and if you have any more questions that we're not covering today, I'm happy for you to contact me. So in case some of you are not aware of the Bristol Robotics Lab, is a venture between two universities at Bristol, which is a very nice city in the UK. On a sunny day, it looks beautiful, as you can see on the right side of this slide. And the lab at night looks like what is the left picture here, with what we call the lamp holders. Some old robots are holding the light for us at night. So I lead the Dexterous Manipulation and Wearable Robotics group at the Bristol Robotics Lab. I'm part of the University of Bristol, myself specifically, and our work covers a very wide range of topics, but they all somehow have to do with dexterity and hands. So we've got projects from surgery, diagnosis, physiotherapy, about touch and human-robot interaction, as well as applications in nuclear and space robotics. And I'll touch a little bit upon this. So why hands? Hands is something that we use in every day since we are born, and this is how we learn to interact with the environment. It's very, very important for creating the synapses in our brains and developing as a baby to a toddler and later. We use it to play the piano, to be dexterous, to create music. We use it, of course, for cooking, for surgery, for something really, really small and precise. But we also use it to touch each other and feel each other and be intimate with each other. Without this sense of touch, you don't really have dexterity. And I really like to look at these two what we call homunculi. So the left one is the motor homunculus and the right one is the sensory homunculus. And in these representations of the human body, the biggest a part is, the more of an importance it has for that function. So you can see, for example, that, the mouth is quite big because in the motor homunculus, because we use it to speak, to interact, to eat. But then it's also quite big in the sensory one, especially when it comes to tongue and lips, because they have a lot of sensory instruments on them. And the other part, of course, you can see being really, really big in both of them is hands. We use hands to interact, to grasp, to manipulate, but we also use them to sense, especially. And if you look at specifically in the sensory homunculus, the fingertips are much bigger in relation to the rest of the hand. So as a starting point, hands, and this is because without the hands in the current form, we probably wouldn't have really gone past our primeval age as human species. I started back in 2000, many years ago now, 2012 or 13, looking at how we could improve surgical robotics. And when I say surgical robotics, as many of you might know, it's not exactly surgical robotics, but it's robot-assisted surgery. So we're not really removing the surgeon from the equation here, because the surgeon is very important, because it's something that we cannot really do complete autonomous just yet, at least. So we looked at how we can try to learn from the human hand and try to integrate some of the properties that we have in our hands into surgery. So we looked at creating a surgical system, having a leader and a follower that somehow took inspiration from the human hand. We created a set of exoskeletons that the surgeon would wear. The exoskeletons would track the fingers and the hand and the wrist motion of the surgeon, taking information and then sending that to instruments that looked like miniature human hands. So in the bottom right, you can see one of the mock-ups for them is basically a three-fingered hand that the difference to a lot of what exists so far is that would have many degrees of freedom. It would have in total 13 degrees of freedom as a robot hand. And of course, we cannot forget the necessity for having some way of communicating to the surgeon of what they're touching. So this is why we also integrated haptic feedback system into the exoskeleton. So the exoskeleton is not just sensory, but it also has a way to actuate itself and provide resistance in terms of feedback. So, of course, this is something that was sort of finalized or put on hold at least around 2016, I think. That's quite a while now since then. And the direction we wanted to go from there is to try to improve the ergonomics of such a system. How could you do it that is comfortable? It's something that you can use easy, you can put on easy, and something that possibly could have applications beyond simply tracking the hand, something that could be used, for example, for physiotherapy. So we looked at having lots of other exoskeletons or gloves, if you'd like them, that are more soft and flexible, compliant. So the left one was one of the early efforts in this. It was a leather glove. The one on the right, both of them, they're not leather, they're silicone. And the innovation here is that we looked at making these wearables easy to manufacture and cheap to manufacture. So we basically use silicone sheets that we can laser cut. So within 15 minutes, we can measure your hands, we can measure your length of your fingers, width of your fingers, and your specifically phalanges, update our parametric cut design, and then laser cut the glove that fits your hand perfectly. And of course, then these gloves share the same actuation system. So you could have the same actuation system that can just be plug and play for different ones. That opens opportunities for many different applications. So tracking, surgery, physiotherapy. Imagine having a hospital with one expensive actuation system, but multiple different gloves on the different patients can wear. I mean, you can even have them as disposable in a way because it's not that expensive to make them. Of course, you want to look at sustainability. You don't want to be wasting materials. So perhaps something like small, medium, large would be sufficient in this case. So this is the part of the tracking. We wanted also to look more into the haptics and tactile sensing. So we created 3 different sensors. So the first one on the left was one on the haptic side. So we created what we call fingertip haptic device that you can see is a little tiny pillow that basically inflates and deflates. That also is actuated in a linear fashion. So basically you can squeeze your fingertip or release it. And by combining these 2 modalities, we were able to emulate different scenarios. For example, when you are palpating during diagnosis. So you can have remote palpation. So you can have then wear it as a clinician and try to identify between stiffness or softness. Let's say, oh, this area feels soft, this area feels stiff. There might be tumor here. There might be an abnormality that we want to look further into. So taking that concept further, and especially this pneumatic inflation, deflation of that fingertip, the haptic part, the soft part of this device, we looked at making tactile sensors that using optics-based technology to look at how a membrane deforms using this sort of white dots that you see on the inside, but at the same time, not do just that, but include these pneumatics to try to tune the range of these sensors and therefore the sensitivity. So when you're using these sensors, the new tip in the middle or the espresso on the right side, for example, for examining a breast, you might want them to check on the surface and have them at a specific setting. Maybe you want the membrane to be a bit soft then because you don't push so much on the breast tissue. But when you want to really explore what's happening inside the breast tissue, deep within the layers, you want to inflate that membrane, make it stiffer, and therefore increase the range and the sensitivity for a specific type of exploration. So this is how we can use them to then try to not only sense the surface of an object, but also the volume of it. So, of course, we then looked at how we can use these in a specific application. And this was a project funded by Cancer Research UK in combination with the Research Council in the UK for engineering. And the project was called Artemis. So we started with looking at how robotics will be accepted or not in breast diagnosis. We did a survey with 132 participants, I think, and the results were very positive. They were very, very keen to have something that they could access easily, frequently, and something that could basically make them feel a little bit less shy, a little bit less shame of going to exposing themselves to a clinician to do so. And based on that, we started developing a possible platform for examination that would be completely autonomous. So for that, we needed, of course, something to sense and something to hold the sensors. And throughout this process, and this is where the end user comes in, we had a panel of experts with lived experience that were following our research, giving us feedback, and helping us redesign and rethink the technologies that we're creating. So we started with the two sensors that I showed you already, the new tip and the espresso. The new tip is basically having a camera inside and, just inside the membrane. The espresso, it works in a fluidic way. It basically has this umbilicus, these 7 or 9 tubes that are filled with water that is dyed black. And then this water is monitored by a camera moving right and left, basically giving us information about where the membrane is pushed and by how much. Now, what holds those sensors? This is something that we also developed, and we looked at 2 different mechanisms. We tried to make them as simple as possible with 2 degrees of freedom each, enough to cover the breast surface and the morphology of the breast, because breasts are very different between people, between genders, and they have different shapes and different sizes. So you can see here the first one is called Iris. So that was, of course, as you can see from the name, inspired by the iris diaphragm of a camera and the way that it opens and closes. So it has this 1 degree of freedom that is radial, but it also has another degree of freedom on how the sensors at the fingertips is actually moving. It basically tilts up and down. And these 2 degrees of freedom are basically, again, in a very simple way, allowing us to palpate and cover the entire surface of a breast outside. And the idea that the sensors that can tune the sensitivity are attached at the end of these fingertips is what allows us to explore inside the breast. Again, using multiple sensors for the same object for different aspects, which this redundancy allows us to compare and locate where inside that volume some abnormality or stiffness exists. The second mechanism we called Lotus. You can see the first drawing that we put down on a paper that was inspired by the lotus flower, how it opens its petals and has a bio-inspired, of course, approach, but something compliant and safe for someone who would want to put this on their bodies. Of course, in engineering, it looks quite different than the beginning one, but in essence, it works in the same way, because these 3 fingertips that you can see here are compliant, they're soft, they do have a basic rigid structure inside them, a skeleton, but they're soft to touch and they're covered with materials that would be friendly for the user. So on the bottom right, you can see one of the modalities and on the functions that it would touch, palpate, rotate, and then again, change position to make sure that it covers the entire breast. So both of those mechanisms, the iris and the lotus, are parametric, so they can hold anything between 3 and 8 fingers. So it's about an optimization about how much is it that you want. You want to try to balance the complexity of your robot and therefore the cost, but you also want to balance the other side of the scales, the time and the length of the examination that a patient would, put up with if they were going to somewhere to do this from scratch on their own without clinical support. So end user involvement, as I said, was throughout the entire project, and he focused a lot on discussing which of the technologies they liked, which part they liked, which they didn't. So as some of the ideas, the Lotus was a little bit more organic looking, a little bit more friendly looking than the Iris, which was more mechanical, more robotic, more engineered. But then, of course, what was really interesting that came out of the meetings was that none of it really mattered to the expert. It was more about making sure that the accuracy of the robot was better than a common GP. And we know from the literature that GP, although they're trained on this, it really depends on how long the training was, how good the training was, and it is very subjective as well. Because they just have usually the digital palpation, their own hands. So we're looking into continuing now this project, and we're looking at, of course, expanding not just to women, but also to men, because men are also a big part of the population that do get breast cancer, and they're often overlooked, especially because of the current methods that are used to diagnose cancer in breast. So mammograms are the most common approach, but they are very painful. They are very uncomfortable, especially if you have really large breasts or if you have really small breasts. So the idea here for this project was to make something that was safe, friendly, and more accurate and more reliable, because you can store your data and then have frequent checkups by yourself, comparing your data to your previous time, and therefore detecting any change as soon as possible. So we really were focusing on breast health rather than diagnosis of cancer here. So I would like to move on to a little bit of a different type of project that we're doing, because again, we're looking at dexterity, but in many different aspects. So dexterity can also mean how you insert a needle in someone's body. So there are 3 similar types of application. One is for biopsy of the prostate, one is for treatment of the prostate, which was the brachytherapy, and another one in that different area of the body was a pleural aspiration, which is basically taking out fluid or air from the space outside the lungs when there's a buildup of that and there's pressure. So these 2 applications share a lot of commonalities in terms of approach and in terms of how you would apply your technology to them. But I want to start with, for today, because we don't have much time, in the biopsy. So biopsy of the prostate happens in the way that you can see in the top right image. You have an anal probe, that is the ultrasound, that is inserted underneath the prostate, and therefore it gives you visibility into different camera views that you see on the bottom right. So on the sagittal view on the right, you can see the needle quite clearly. But when it comes to, of course, the axial view, it just is a little white dot. So you have to be quite clever and quite trained in always looking at where you are and always have awareness of your surroundings as a surgeon. Now the needle itself enters through the perineum here, and it can be, it's obviously a full anesthesia, not local anesthesia for this procedure. You don't feel anything, but the surgeon has to do some really interesting manipulation techniques that I'm going to talk about later. So why do we need to care about this? Cancer in prostate is the most common one in individuals assigned male at birth. It's more than 52,000 per year in the UK. It's the second common cause of death. The good news here is that if you diagnose it early, it doesn't lead to death. So biopsy is really important. Of course, the challenge here is that this procedure is full of shame. People don't want to actually go and do it. They don't even want the digital palpation. That is the first step towards this diagnosis. It involves a lot of discomfort, and there are, of course, a very, very long waiting queues, be it from the aftermath of COVID or from all the different strikes that we have and the low paid doctors that we're facing now, the crisis. So we don't have often all expertise and availability of surgeon. So what we try to do here is first model the needle, and specifically the two ways of how the needle would be deforming if you were manipulating its base. So the way that they manipulate the needle, the surgeons, is that basically they're moving up and down to try to reach a different part of the prostate, or they rotate it. And they rotate it because, as you can see on the top left here, the needle is not uniform. It has a bevel tip, which means it has non-uniform forces acting on the surface of the tip as it's entering the tissue. So when you, for example, are pushing it forward and the bevel tip is looking down, the needle is going to go upwards inside. So if you want to basically avoid an obstacle in a way, like a calcified region of the prostate, all you have to do is approach the region, go up to circumvent it, and then rotate axially to then start going down again. So these two type of manipulations, we looked at how we can model the needle and then experimentally verify these models, which ended up being really, really good. And everything is published for this in these two different venues, so you can see at the bottom of the slide. The next step was to look at how we can model the interaction between the tissue and the needle. And for that, we used model predictive control and adaptive control for the robot arm. We used a shank robot arm, and we simulated the tissue using ballistic gelatin. And for that, we used 3 different types of consistency of gelatin and water to try to emulate different properties of the human tissue. So these 3 different blocks will basically cut in pieces and then put together to try to emulate the inhomogeneity of the tissue. So the estimator module will then generate updated estimates for the parameters of the kinematic model of the needle's tip, the system, the state of the system, and the state of the system. And then they would be fed to the model predictive control. Then this would autonomously decide the optimal insertion axially and the rotation velocity of the needle, which would then send to the robot arm, as well as a motor at the end, at the base of the needle. So you can see here in the videos at the bottom how the tip of the needle enters the tissue and is trying to reach the end target. So we did user studies here. In some of them, we only showed the target to the user, and in some of them, we also helped them by following this trajectory, this dotted trajectory that was basically projecting the optimal straight line trajectory to the target. What it was quite interesting here was that surgeons were a little bit more precise than users that had no experience in this platform, but not by much, really. And I can show you. Okay, sorry, I shouldn't have. So, and then we compare this to the robot itself, doing it in an automatic way completely. And just by comparison, it was about 5mm accuracy for the best accuracy was 5mm for the humans, and 2mm was the worst accuracy for the robot. So we can immediately see that it was really interesting. Just by this simple system, the robot itself had immediately improved accuracy. We also looked at the possibility of such a system to be used for training surgeons, and therefore we did a user study on the way that people used and manually manipulated the base of the needle. So you can see here the 3 examples, an example of one of the users, but it was very common sort of strategy that they were using. So the left one is the X coordinate of the needle tip, the middle is the Y, and the one on the right is the Z. So what happened is by having these two cameras, usually the user would be looking at one dimension and trying to really track that and keep to the correct straight line path. But then what happened is that they completely missed the other one. And this is something that the surgeons currently are doing. They trained for years to try to do just that. But the robot could do that really, really easily. So this was really interesting. And it can also, become a training system that you can score them, obviously, and help them improve their techniques. So the goal here, of course, was to try to automate the biopsy procedure completely. It's something that is quite simple to be done. And the surgeons of our team were saying that if in 10 years' time it's still being done by surgeons, it would be quite a sad scene, really. So you can see here how the robot is doing it completely autonomously. It's basically looking at reaching the target in a straight line path, optimizing the trajectory and manipulation, rotation of the base. And next steps here, of course, would be to look at something that we haven't looked at so far. So we looked at different types of tissue as you're inserting the needle, and the adaptive controller is where it actually really helped, because the tissue wasn't uniform. The tissue between one man to the other is not the same, but the tissue between the same person is also not the same because it has calcified regions. And when you hit a calcified region, everything changes. So we believe that our model will still hold in these conditions, but it remains to be tested. So moving on, and just very brief talk about how human-robot interaction and our work can also have some applications in, for example, space, is where we looked at the delays in communication and how they could be mitigated when you're operating between Earth and the Moon, or orbit and Mars, for example. So in situations where you have maybe a 2-second delay or even minutes delay. So the common approach in these cases is that the astronaut basically does something, waits for the robot to respond and do it, and then stops, waits, pause, and then does the next step. Obviously, this is really time consuming, and you don't have a lot of visibility on, when something happens and something gets destroyed, on how you can correct it fast before it's detrimental conditions. So we looked at how we can mitigate the delays and how we can make the system more trustworthy. So one of the first, of course, experiments we did was to have some simple tasks like draw a line or put something in a hole. And we tried it with different delays, and we were hoping that haptics would be the answer to it. Where maybe to our surprise, it really wasn't. But what we found was that it was actually quite good at low delays. It was still helping us, but above a certain threshold, it was making haptics would make it really much worse. And this was because, I think you can see it in the video here, if I can play that. But I think I can move it towards the end. Basically, you were expecting to be at a certain position, and suddenly the robot would just kick your hand away because something was happening that you were not expecting. So with that, then we looked at how can we help that to model first some of the experiments that astronauts are doing, and then trying again to replicate them using model-mediated control. Now we still have haptics, but you don't actually operate the delayed system. You operate a modeled system that is then transferring itself to the real system. So first we modeled regolith, which is basically another word for moon dust. And we verified this in the lab on how it can fall, about the consistency and the consistency and the rate that it was falling through a funnel when you're scooping it, for example. And then we looked at, as I said, the model-mediated manipulation and different tasks such as pressing down, dragging, and scooping, which is, for example, what they want to do when they want to take a sample out of the surface of Mars. So you can see some of the experiments here and how they were done. They were done with using a KUKA robot operated by a Haption 6D desktop virtuos system. So this is about by the way to be presented in IRA, so I won't take too much time on that. That is happening next month. So one other big part again, and closing a thing with the end users requirements for these projects is that we talk to 13 different operators for nuclear, underwater, and explosive devices, but as well as 3 surgeons, because we felt that there was a lot of overlap between operators in extreme environments and surgical and surgeons who were using robot-assisted surgery. We looked at what would be the low priority requirements, mid priority requirements, and the high priority requirements. And we interestingly discovered that among all of these different areas, there were very, very similar requirements. And I'm just going to say just one point that was really interesting is that all operators apart from surgeons were happy to work in a delayed conditions environment when you have delayed communication. They were happy to try to mitigate it with different strategies. However, that wasn't true for the surgeons. They would be completely denying to work on a system that had delays. And I think obviously that might make sense because a human life is at risk here. But interestingly, not when you have astronauts in Mars or Moon, you can't have a surgeon there. So in these situations, you would have to try to deal with something like this. And I think it's in the future to try to help them go across that obstacle. And with that really quick whistle-stop tour of what we're doing, I'd like to thank, of course, everybody that has contributed to this research and all my amazing students and the 4 clinical collaborators that you see on the right side of the slide that have really contributed with the ideas and the support. So thank you very much for listening.
Brilliant. Thank you very much, Antonia. Any questions for Antonia? Okay, we have a question on the chat. What's the simulator you use for the moon dust?
Okay,
and
so let me go
the
back to
accuracy of the simulation of those dust flow dynamics.
So we based our work on an existing model that was published in 2021 at ICRA, and that was the Pereira and Schmidt model. Their model was somewhat, in a way, more accurate than ours, but our idea was to try to make it real time and simplify that, but also extend it. So unfortunately, I can't remember the specific numbers for accuracy, but this is published in this journal that you can see at the bottom. It was published about 6 months ago. So please do refer to that because I don't remember the numbers by heart.
Any more questions?
I have a question.
Go ahead, Rachel.
Thank you very much for your really interesting talk. I'm a little bit curious about the latency threshold that you were describing for haptic feedback no longer being useful. Do you remember offhand at what point it became problematic?
So it's in this video. I think so I actually, yeah, I can tell you because we look at these 4 different that you can see on the screen now, and I think 600 milliseconds was okay, but anything from 2.6 seconds and above was just basically completely making everything much more difficult.
Thank you.
And it was really interesting, because at that point, that was 1 year into the project, and we had to completely change direction because we thought haptics was going to solve it. was going to basically be the answer. And then we realized, oh, we were a little bit too excited about haptics. We need to now try to look about exploration. And then we changed a little bit the direction into looking at the trustworthiness of the whole idea and how we can use haptics to make the system more trustworthy, which I feel that now we have reached it with these the final experiments where we're using model-mediated control, which includes haptics to control something that has delay, but the user doesn't actually get affected by the delay anymore.
Just to follow up on that, have you implemented any time domain passivity approaches?
Have we? No, I think that was one of the steps that we were looking into, but we didn't. Not at the moment, at least, maybe in the future.
I have a question for Antonia about the medical devices. How close are these devices to being actually used in the NHS or a hospital in general?
Yeah, that's a good question. So, you can see from this slide, our research and our results were picked up by the press, and we were really excited because people showed a lot of interest in them. But the reality is that this was all in the lab. And now, next step would we have to be to create a more substantial prototype, prove how that works, then prove how that would work in either animal specimens or cadavers, then get more funding and move it forward. So at best of cases, this is looking at a 10-year scale, which is a little bit sad. But what is interesting is that we experienced that during COVID. When a lot of funding and a lot of effort goes into an area, you can have results much, much quicker. But for COVID vaccines to be developed, a lot of other areas suffered, and because funding was drawn from them. So I think this is the case for everything. If there's a lot of interest in one area, things can be sped up. Otherwise, the process is quite long.
Yeah, and this can take way too long in terms of funding as well.
Not to mention, of course, that working in a university and research and publishing, which is what I like to do, I like to have all my work open source. But when you do that, then you basically could kill off good research, because if it is all in the public domain, no company will want to adopt it. And if no company wants to adopt it, how is it actually going to reach the end user? So, I'm fighting between those two ideas. I want to get things to the medical market to benefit patients, but I also want things to be open source for other researchers to benefit from. So it's a conflict, isn't it?
Exactly. Do you have any commercialized devices at the moment, or are they still in progress?
No, everything is in progress. We are trying to revise our approach towards that, because we have been very open source, as I said before, and we have looked into different things, and the answer we get is like, yes, this is almost ready to go, but you kind of have to change your fundamental technology so we can patent it. Otherwise, there's no interest.
Yeah. Okay. Thank you very much, Antonia. It was really amusing to see how this progresses. I hope it goes very well in the future as well. Good luck for your research, and thank you very much for joining us for the talk today. And thank you very much all for attending the talk. If you would like to get in touch with Antonia, please feel free to contact her. And thanks all for joining us today, and see you in 2 weeks with another episode of FI Talk. Have a great week ahead.
Thank you.
See you.